this mini lecture, I want to talk about how volcanoes fit into the context of plate tectonics. In most cases on Earth, volcanoes and their location, their types and location, are driven by where they are in relation to different plate boundaries. So the first thing to realize is that the distribution of volcanoes on Earth is not random. They're not just sort of equally distributed everywhere. Instead, there's a definite pattern. We find that most volcanoes occur along subduction zones, so that's along a particular type of plate boundary. In this figure here, they're illustrating what's sometimes called the Ring of Fire. It's the fact that we have active volcanoes on the edges of continents, basically where the continent meets the Pacific Ocean, pretty much all the way around the Pacific Ocean. That's not the only place we have volcanoes. Obviously, here's Hawaii, and that island is made entirely of a volcano. But a lot of the volcanoes occur along subduction zones. So what we're going to do is we're going to talk about volcanoes occurring in different plate settings, and then we're going to talk about what drives those volcanoes. What kind of magma are we going to have there? What kind of melting is happening? So we're going to reach back into chapter 4 and think about types of melting and rock types and put them together with the volcanoes and then place them with the plate boundaries. So we're going to start looking at subduction zones. So remember, subduction zones are a type of convergent boundary where two plates are converging or going towards each other. There were two types of subduction zones, and we're going to start with the one where we have an ocean plate subducting underneath another ocean plate. So you've seen this figure before in previous PowerPoints. So here is the ocean plate, and this is the one subducting underneath the overriding plate. So we've talked about several different ways in which melting occurs, and in the last chapter we were talking about melting occurring when water was added to the rock, and that happens in subduction zones. So we were focused right here where water comes off of this subducted slab and travels up into the mantle and allows the mantle rock to melt without adding any heat. So once we get that magma, so we've got the magma forming here, right? It's rising up, and then because this rock here that it's traveling through is basically basaltic, this magma can rise up through that basaltic rock just driven by density differences. So remember, buoyancy was one of the factors that allowed magma to actually make it to the surface, and buoyancy was defined as the tendency for a less dense substance to want to be on top of or rise through a more dense substance. So we have mafic magma that formed here, and that mafic magma is then rising up through mafic rock. So again, to remember the process of addition of water, if it happens in the mantle, we're melting ultramafic rock, right? So our source rock is ultramafic. And that means the magma that's created is mafic. So again, mafic magma rising up through this lithospheric area here and the crust. It's able to easily rise all the way up and erupt, and we end up with volcanoes here also created by mafic magma. So we have another kind of subduction zone, one where we have the ocean plate, which always subducts, but this time the overriding plate, the plate it's subducting under, is a continental plate. And in that case, we have two separate steps of melting. So this is a more complicated process. The first step is exactly the same as the last slide. We have addition of water, which causes melting, right? We're melting the mantle rocks, and that creates the mafic magma. So that is right here. Same thing is happening as was happening on the last slide. The difference between this slide and the last slide is that the crust on top of the mantle right here is no longer oceanic. Instead, it's continental. Continental crust, however, is intermediate in composition. So we have intermediate rock, and it turns out that that's less dense than the mafic magma. So that means that the mafic magma will just sit here and not move up through the continental crust. It's very hot though, and so instead of moving up, what it tends to do is heat up the continental crust. So if we heat up the continental crust, we begin to actually melt the crust. So that is the second step of melting that happens in a subduction zone. This process is happening through the addition of heat, and that heat is coming from this ponded magma down here at the base of the continental crust. So since we're melting rocks in the crust, which are intermediate in composition, the magma we're going to create now is a felsic magma. So we end up with little pockets of felsic magma forming, and then what normally happens is that the mafic magma that has ponded mixes with that felsic magma, and that creates intermediate magma. Now we have intermediate magma rising up through intermediate crust. So now the magma is less dense than the rock, and it can rise up and get to the surface. So the volcanoes that we find here are made of intermediate magma because of that mixing. So in subduction zones where we have an overriding oceanic plate, we have one step of melting the mantle, creating mafic magma, which rises to erupt. But in this second type of subduction zone, where we have continental crust as the overriding plate, the mafic magma that's created from addition of water gets stuck at the base of the crust. The heat from that magma melts some of the continental crust, creating felsic magma, and then the mafic and the felsic magma mix together and eventually rise up to erupt as volcanoes, and the volcanoes then are made of the intermediate magma. So there is a third type of convergent plate boundary, and that's a collision zone. We're not going to talk about a collision zone here because that's not a place where you get volcanoes. So we're just putting volcanoes into the context of the plates. So the next boundary to think about is the divergent boundary, a place where two plates are moving away from each other or rifting. When we talked about this, we talked about how the first part of rifting always involves breaking a continent in two. And that's in this picture up here. So you can see we have one continent, and these white arrows on either side are stretching it and beginning to break it. That causes this part of the crust to thin, this part of the crust and lithosphere to thin, and that is what leads to decompression melting. There's less rock sitting on top of the mantle, and so this area here in the mantle feels less pressure and begins to melt. So again, there are two steps of melting, much like the second subduction zone that we talked about. As you melt the mantle down here, you are going to make mafic magma. But that mafic magma is going to get stuck again because we have continental crust. So you end up with that mafic magma ponding at the base of the crust, adding heat to the crust and melting some of that crust. So that creates felsic magma, right? So we had mafic magma created from melting the mantle, felsic magma created from melting the crust. So again, they mix together and create intermediate magma, and we get mountains like Mount Kenya and Mount Kilimanjaro in the East African rift made of intermediate magma. So this is the early part of a rift, right? Before it becomes an ocean. So the second type of divergent boundary, it's still a divergent boundary, but it has matured enough that it's become a mid-ocean ridge. So we've separated the plates enough that we have got a full ocean here. The melting process is still the same, still decompression. You're still basically having less rock pushing down here than you are down here. And so you're still melting here, but now there's no continental crust. So this magma can move right up and erupt at the surface to create the new seafloor. So we make mafic magma, and it's a mafic magma that erupts. So this is like the one-step melting, similar to that first subduction zone. No continental crust involved means that things are much simpler. Now we can also have volcanoes occur in the middle of plates. So we call that an intraplate volcano, the interiors of the plates. They're not as common. Most volcanoes, as I said, occur along subduction zones. And secondly, along divergent boundaries, those rifts. The type of melting that's associated when we get volcanoes occurring in the middle of a plate is also decompression, as it was for the divergent boundary. We've talked a little bit about mantle plumes. We talked about creating hotspot volcano chains in Chapter 2 when we talked about measuring how fast the plate was moving. So these volcanoes are not associated with plate boundaries. Instead, they're associated with mantle plumes. There are also things called super plumes, and we didn't talk about those when we talked about the hotspot trails, but we'll talk about them now. So what happens in intraplate volcanics, where we're not along a plate boundary, and we have a super plume come up. So here in this figure down on the bottom, we've got a super plume here, and it's moving up because it's hotter than the surrounding rock. So as it moves up, it's this really enormous amount of rock. It moves up, and as it gets closer to the top, so we're over here now, it begins to melt through decompression. Again, less rock down, pushing down on it there than there is here. But this is such a huge amount of magma that we don't just get a single volcano. It's also mafic magma. We're partially melting the mantle. So remember, the mantle is ultramafic. That means the magma is mafic. So it's a very fluid magma. So this very fluid mafic magma creates what are called flood basalts. And as you can see in the top picture here, the magma, instead of coming up in a central area and creating a cone, actually comes up through long fissures or cracks in the crust. So you can see we have a long crack here and here, here, and here. And magma floods out of all of those, and it's so fluid it spreads really easily, and it just coats the whole area. That's why we refer to it as a flood basalt. And that is happening simply because there is so much magma being produced at one time because of how large this area is of the superplume. So we call them flood basalts because they're flooding the landscape just like water would flood the landscape. Now the superplumes also have tails. They're basically still rising magma, but it's a much smaller amount, right? So here's the flood basalt province that was created. Remember, plates are moving, but the mantle is not. So the plate has been moving this way, It has basically taken that flood basalt province and moved it away from where the plume originally came up. And now, as the plate has moved, individual volcanoes are being created. So we've got one here, and then the active one here that's still on the plume, the hot spot. So the plate keeps forming a volcano and then moving it this way. That's why we end up with that chain. You should remember that from chapter 2. So basically the flood basalt province is actually connected in many ways to the hotspot chain that we talked about previously. This is a map over here of a flood basalt province in the U.S. called the Columbia River flood basalt. So you can see it's been exposed through the Columbia River Gorge. That brown area here, this is all flood basalts, huge area of flood basalts. And if you look at the photos, you can see, especially in this lower photo here, how we've got these multiple layers. They're very flat lying. They did not form any kind of a central cone, right? They just flooded as if they were water. They were so fluid. And then this picture here shows you how very thick some of the layers can be. So we can see how flood basalts and the hot spots are connected if we look at a map. So we've got, here's a flood basalt area, and then we've got a hot spot trail that leads here. Here's the Hawaiian flood basalt province would have been somewhere up here, but it was subducted away because there's a subduction zone right there. We've got flood basalts here, the Deccan traps, and the hotspot trail that leads to them. We've got hotspot volcano here, and the flood basalts were on one continent when it was together, but it has spread apart, so we've created basically volcanoes in both directions. And then in the Caribbean you can see the same thing. So this is another place. It's not really a plate boundary, but it's still in the context of plate boundaries, because as the plates move, we create these hotspot chains away from these flood basalt provinces. So it's again putting that type of volcanism into the context of plate tectonics. The reason we have these hotspot chains connecting the flood basalt province is because of the way the plate was moving.